So far in our study of integration, we've looked at how to create approximate values for definite integrals, or the areas underneath a graph, or the subtle shadings of positive and negative contributions to a total. And we've done that using left and right-hand Riemann sums. Now, those who have seen integration before are quite happy, I'm sure, at this point, going, oh good, let's get to the integration stuff. We've seen it, let's use it. For those who haven't, don't worry, we're going to get to that next week. We're going to get to what in practice tends to be an easier way to do integration than what I've shown you this week. But we can't get there yet, and it's worth mentioning that we can't always get there at all for some examples. So for those who have seen integration before, these integrals that you see here, e to the minus x squared, and this other integral here, sine x over x dx, these are famous integrals for which we won't be able to use any shortcuts. There will not be any antiderivatives for those who have seen it ahead of time, and there's going to be no shortcuts to finding the areas underneath these graphs or the sums of these functions times delta x's. We're going to be stuck. So where does that leave us when we have these functions that appear very, very frequently in science and especially exponential and statistics everywhere? If we want to evaluate these integrals of these functions, so over some area, over some interval, what's the sum of those function values times delta x? We could certainly use left and right hand rules. Absolutely. We've seen those already. However, we'd like to have as an estimate as possible. So left and right hand Riemann sums, let's emphasize this, with a finite n value. So in other words, a fixed number of intervals, 50 intervals, 100 intervals. And what we'd like is the most accurate estimate we can get, which of course makes us think, wait, we've done that already. If I want more accurate estimates, I just use more rectangles. In fact, we would let n go to infinity, use lots of them. If I have to use a computer, I'll use 10 million intervals. It'll be fine. Well, you can do that, but as someone who also teaches a numerical methods course for the engineers, a better way to pose the question is to ask, not can we make these estimates more accurate? Sure, we can by doing lots and lots of work. The question is, can we do it more wisely or more efficiently? In other words, for the same amount of work, can we get a more accurate estimate of the area underneath the graph using a finite number of intervals? So the goal here is to generate accurate estimates. I think we actually basically said it there. I'll just say it again here. Accurate estimates. And again, notice the word estimates here. That's coming from a finite number of intervals. So not the definite integral that we've been looking at so far, as efficiently as possible. Okay, least work for the most accuracy, and we'll just leave that as implied. And I'm going to claim that left and right hand rules are not the way to go, otherwise we wouldn't be looking at this particular unit. All right, so let's take a look at a Riemann sum calculation when we use the midpoint of each interval. So let's just take some arbitrary function here. Let's make that a little prettier here. Oops. My eraser. There we go. Let's see if we can make that a bit prettier, like so, and like so. And so let's say our function does that. And we break it up into 3 intervals. And let's try to do that over here as well. I think we might just compare the left-hand rule and the... oops, that really was dysfunctional. Maybe the left-hand rule and the midpoint rule. So 3 intervals again. If we were to use the left-hand rule, or left-hand sum rather, with 3 intervals, the area we get is represented by these rectangles. These 3 rectangles here. If we do the midpoint rule, the rule there says on each interval, don't go to the right, don't go to the left, go to the midpoint. Go up to the graph there and build a rectangle out of that height. go to the midpoint, go up to the function, build a rectangle out of that height. Go to the midpoint, build a rectangle out of that height. And just looking at this, it's very clear that on the left-hand rule for this example, we're going to have an underestimate multiple times. These are all underestimates or missed area. Or missed areas. However, when we look at the midpoint rule, we're going to have underestimates here, sorry, overestimates and underestimates mixed. The area that we get from the rectangles using the midpoint rule is going to be sometimes an overestimate and sometimes an underestimate. And those are going to cancel each other out, because if I overestimate a bit here but I underestimate a bit here, I'm going to be closer than if I'm constantly underestimating or constantly overestimating. So this midpoint rule will produce a more accurate estimate. And this is true in general. A more accurate estimate of the exact area under the curve. So if we look at that right away, we're better off if we use midpoints. Let's see if we can make that a bit more concrete here. In fact, we can even get more accurate. Let's take a graph here again, like so. And what kinds of functions will the midpoint rule produce a value that is exactly equal to the integral? Well, we can get some inspiration actually from that last diagram. It would be, the midpoint would give us exactly the right area if the overestimate and the underestimate were the same every time. And that would happen if our graph were linear. Doesn't matter how many divisions I make of a linear function. If I take the midpoint, the underestimate and the overestimate will always balance out if I split it correctly in the middle. So take this sketch with a grain of salt. So for any linear function, we would have that property. And contrast that with the left and right hand rules. The left and right hand rules would do pretty awful jobs at finding the area or correctly and accurately estimating the area under this graph, because the left hand rule would always be an underestimate. The right hand would always be an overestimate. The midpoint is that Goldilocks thing of being just right. All right. Now it is possible, it's rare, but it's possible for the midpoint rule to get something less accurate. And it's worth trying to think about this before you see the answer here. Let's take a look. So let's just make 2 intervals, keep it simple. What kind of behavior would we need for the function to do poorly with a midpoint estimate of the area and do better with the right or left hand sums? I think the recipe there, the way to think about it is to think, well, maybe the function's well behaved until it gets close to the midpoint. So maybe the function does something really bizarre like that, and then goes along, and then maybe, yeah, it goes up again. And so for whatever reason, when we use the midpoint rule here, yeah, we get this crazy overestimate of the real area. It just makes no sense whatsoever. But this graph shows that at least the midpoint rule isn't always better than the left and right hand rules. We can find degenerate examples where the midpoint isn't as good. However, it's very important to note that even if you had a function like this, for whom on these 2 intervals the midpoint rule wasn't very accurate, if we reproduce the same graph again and used more intervals, well, then the midpoint would do a fantastic job as we go along. It would actually, again, do better if we had more intervals. So the midpoint rule wouldn't be fundamentally flawed. It's worth noting that it's not 100% guaranteed that it's going to produce a more accurate area estimate than the left-hand rule and the right-hand rule. It just does it almost all the time, and certainly for any reasonable functions with lots of intervals, the midpoint rule would be better in almost all cases, but not every single case.